Now we're ready to prove the famous mean value theorem. Our hypotheses for the mean value theorem are that f is continuous on the closed bounded interval from a to b and differentiable on the interior. If that's true for f, then our conclusion is that there exists some interior point c where f prime of c equals f of b minus f of a divided by b minus a. Notice f prime of c is the slope of the tangent line to the curve y equals f of x through the point c f of c. So this is the slope of the tangent line at c. Whereas f of b minus f of a divided by b minus a, that's the slope of the secant line passing through a f of a and b f of b. In other words, it's the slope of the line that connects the endpoints of our function over this domain. Let's immediately rule out one case. If it were the case that f of a equaled f of b, then the mean value theorem reduces to Rolle's theorem. Because if f of a equals f of b, the right-hand side of our conclusion is just 0. We have 0 divided by b minus a. And Rolle's theorem told us that if the function had the same value on the endpoints, there was an interior point where the derivative was 0. So we know that there's a c where f prime of c equals 0, and that's what the right-hand side should be. Therefore, the mean value theorem is like a bigger version of Rolle's theorem. Okay, now let's imagine that our function doesn't take the same value on the endpoint so that we're not just looking at Rolle's theorem again. Here are two such functions. Let me go ahead and sketch the secant line passing through the endpoints. It looks like this. Just based on this picture, you can identify kind of two zones where it looks like tangent lines to the curves would be parallel to the secant line. Let me just identify one of them because, again, our conclusion doesn't tell us where C is, except that it's in the interior. It doesn't tell us how to calculate C, nor does it tell us how many possible candidates we could have for C. It just tells us that there's at least one. So here's one that works. At this point C, the slope of the tangent line is the same as the slope of the secant line through the endpoints. In other words, those two lines are parallel. In the picture on the right, here's our secant line through the endpoints. And in this picture, to me it only looks like we have one candidate. So there's our point C where the tangent line is parallel to the secant line through the endpoints. We'll continue discussing this function on the next slide. Let me just look at these pictures though and tell you how the proof is going to work. What we're going to do is create a function which measures the difference between our original function, this blue curve in here, and the secant line. So we start on the left with a difference of 0 because both the function and the secant line pass through the left endpoint. Then in here we might have a positive difference, a negative difference, and then in here we would have a difference of 0 again. Same story on the right. The difference between this function and the secant line is 0, then it's positive, and then it comes back to 0. Notice it's 0 on the left, 0 on the right, and that should make you think of Rolle's theorem. So what our technique is going to do is basically tilt this picture so that we can apply Rolle's theorem. Okay, to measure the difference between our function and that secant line, I need a description for the secant line, so let's write the equation of that line through the endpoints. Often the first place people's minds go when I say equation of a line is y equals mx plus b, that's slope-intercept form, but I would advertise here the point-slope form of a line. So we can write a line as y equals m times x minus x naught plus y naught, where x naught and y naught is any point that lives on the line. If I chose the y-intercept, this would reduce to slope-intercept form. But what I'm going to do is use this form and take the point on the line to be a f of a, because I know that there's at least 2 points that I can name on the line, the left endpoint and the right endpoint. You would get the same result if you use the right endpoint. With this setup, the secant line through the endpoints has this slope, that's the secant slope, times x minus the known x coordinate plus the known y coordinate. Now we need our function that's measuring the difference between our original function f of x and the secant line. I'm going to call this d of x for difference, and it's going to look like d of x equals f of x minus this whole expression right here. As we saw on the picture a minute ago, with this setup, D is 0 on the left and right. So now we can proceed to use Rolle's theorem to finish the proof of the mean value theorem. So given this expression d of x in the middle here, notice d of a is quite easy to compute. You get f of a minus the slope times a minus a, well that's 0, minus f of a, those two cancel out and you get 0. A little bit more work shows that d of b is also 0, which we would expect because both our function and the secant line pass through the endpoints. D is the difference of f, which is differentiable, and this line, which is also a differentiable function. So D is differentiable. Since D satisfies the hypotheses of Rolle's theorem, I know there's some interior point C where the derivative of D at C equals 0. But what is D prime in terms of our function in the secant line? D prime is just f prime minus the derivative of this line, but that's just going to be the slope of the line. So D prime is f prime of x minus f of b minus f of a over b minus a. You plug in c, the left is 0, so I could solve now for f prime of c and get f prime at that interior point c is equal to the slope of the secant line through the endpoints. And that finishes the proof of the mean value theorem. So as you can see, we needed the interior extremum theorem to prove Rolle's theorem, and we needed Rolle's theorem to prove the mean value theorem. Darboux theorem was really just an extra theorem that I think goes well with these other three, but the real chain of implications here is the interior extremum theorem, Rolle's theorem, and then finally the mean value theorem. Now let's look at how to use the mean value theorem to prove a couple of statements in calculus that we often take for granted. So the first statement is, if g is differentiable on some interval, here I really mean the closed bounded interval from a to b, and its derivative is always 0, then g is a constant function. You might be tempted to say, oh, that's obvious because if you integrate a function whose derivative is 0, it's a constant, but actually we need this result to have a better idea of how to do those antiderivatives. So this is really like a preliminary result that we need before we start trying to come up with antiderivatives of functions. The second one goes along with that. If f and g are differentiable functions and their derivatives are always the same, then those functions are the same except they might differ by a constant. So if f prime equals g prime for all x in the closed bounded interval from a to b, then f equals g plus a constant. It's like a translated g. This second one is really important because when we compute an integral, say that I know I want to do the integral of x squared dx, and I say that's x cubed divided by 3 plus a constant, we're actually using this result. So again, these results need to be shown before you try to appeal to antiderivatives because we actually build off of these two results our notion of how to integrate by hand. Let's prove each of these. We're just going to use the mean value theorem. They're pretty short. For this first one, I'm going to work with the left endpoint A and then choose any other point in the interval. Let x be greater than A and less than or equal to B. By the mean value theorem, there exists a point C between A and X. So here I'm thinking of A and X as forming their own closed bounded interval, where g prime of c is equal to g of x minus g of a divided by x minus a. Our hypothesis, though, is that g prime is always equal to 0. So now I know that the slope of the line through a g of a and x g of x must be equal to 0. This tells me that 0 must be equal to g of x minus g of a, or in other words, g of x equals g of a for all x in a to b. Hence, g of x is a constant function. Whatever the number g of a is, that's the value that g takes across the entire domain from a to b. Now let's look at the second one. If f and g are differentiable functions on the closed bounded interval from a to b and they have the same derivative on this interval, then f and g differ by a constant. What we're going to do here is define a new function to be the difference between f and g. So let's let h of x equal f of x minus g of x. But then that tells me that h prime of x is going to be f prime of x minus g prime of x, and that's going to be 0 for the entire domain. The first problem now tells me that h is a constant function from which the result follows. So from the above, h of x equals a constant k for some k in R. Hence, f of x must be g of x plus k. And again, this result leads to a statement about how we compute integrals using antiderivatives. Namely, if I know one antiderivative, I know all of them because they're all going to differ by only a constant. So both of these results give us some fundamental notions that we use elsewhere.